Okay, hello everyone. Welcome to the problem solving sessions for Introduction to Automata Languages and Computation. So, in this week, we are going to continue with where we left off last time. So, let me get a just a second. Okay, so last time we saw what is called, we saw what are context free grammars. And in particular, we saw a specific type of CFGs which is called Chomsky normal form. So, this is also called CNF. So, we saw a couple of examples where, given any grammar, we can equivalently convert it into the Chomsky normal form. So, now we'll look into yet another special type of CFG. It's called, okay, sorry, just a second. Okay, so it's called Greibach normal form. Okay, or GNF. So what are the rules of this grammar? Let's recall. So you have a start variable, you have a set of variables, you have terminals, and a set of rules. So in general, for any CFG, you can have a production of the form A gives ABC, or A gives a string of terminals, and so on. But yeah, but Greibach normal form is special in that you can only have some restricted kinds of productions. So, for example, you cannot have if A is some terminal, which is some variable which is different from the start variable, then you cannot have A gives epsilon. So these moves are not allowed. This is similar to what we did for CNF. In CNF also this move was not allowed, and it's the same case for GNF as well. But you can have moves like S gives epsilon. So this is allowed. Only the start state can go to epsilon. Further, you cannot have strings, you cannot have productions of the form A gives BCD, where these are non-terminals. So any product of non-terminals will have to be preceded by a terminal. So this is allowed, but at the same time you can't have AB BCD, because the rule says that you can only have one terminal at the beginning. So basically any production will look like uh, A gives A, which is some terminal, or A gives a terminal followed by a product of non-terminals. Only these kinds of rules are allowed, and only the start variable may go to epsilon. So if the grammar, if the given grammar satisfies either of these three conditions for each of the production, then you say that it is in GNF form. So this is said to be in GNF form. So what we're going to do is we will try to convert given grammar into the GNF form. Okay. So let's start with an example. So yeah, you're given three grammars here. So let's look at A. A gives A's of the form, S gives AB, A gives the terminal A, and B gives the terminal small b. So the question is, which of the three are in the GNF form? Okay, so let's check this one by one. So let's look at the first grammar. So this is S gives AB, A gives A, and B gives B. So let's identify which of these rules are in the GNF form. So this is something that it allows. So it allows you to take a non-terminal and simply produce a terminal. So this is allowed, this is allowed, and this is not allowed, because you can't have that variable simply gives a product of two variables. It has to be preceded by a single terminal. So this is something that is not in the GNF form. Okay, so yeah, so A is not in the GNF form. let's look at B. So B has S gives A, and A gives epsilon. If we look at the first production, then yeah, this is definitely of in the GNF form, because it is a product of terminal followed by a non-terminal. So okay, so I just need to charge my Apple Pencil for some time, just a minute. So maybe you can think about it until then. You can see whether B and C are in the GNF form. I'll discuss in a minute. Okay. So yeah, let's see the answer. So like we said, this is in the GNF form. So this is not a problem. But A gives epsilon is not allowed in the GNF, because you're only allowed to produce epsilon from the start state. So this is not a valid production, and hence the entire grammar is not in GNF form. Now let's look at the third grammar. So you have C gives SAA and A gives A. So now, uh, yeah, A gives A is a completely valid production, because it's just a non-terminal that produces a terminal. So this is allowed, but this one here is not really in the GNF form, because uh, you are not allowed to have terminals after the non-terminal, and at the same time your non-terminal should be preceded by a terminal. So this is not in the GNF form, and hence the grammar is also not in GNF. So in this case, A, B, C, neither of them are yeah, please read this as small a. Okay, so by this we mean small a, small b. Okay, I hope that is understandable. So yeah. Okay, so we saw that neither of these is in the GNF form, so the answer is D, none of these. Okay, so if that is clear, let's see that if a grammar is not in the GNF form, how do we convert it into one? So yeah, so here you're given a grammar which is S gives, either it gives ASP or AB or BB, and the question is, how many minimum productions do you need to add in order to bring it into the GNF form? So it is possible that for the same GNF, for there could be multiple GNFs for the same language, and all of them could be valid, but in this question we are interested in making minimum number of additions to the given grammar and obtain the one that is GNF. So I'll wait for a minute, and yeah, please do think about it. Okay, so let's see. So you have S gives ASB, you have S gives AB, and you have S gives BB. So let's identify which of these are in the Greibach normal form. So let's look at the first one. Here you have a terminal followed by a non-terminal, that is okay, but then you have a terminal at the end, so this is not in the form. So this is not in the GNF form. Similarly, for the next two productions, you have this is a product of two terminals, so this is also something that is not allowed, because you're only allowed to have one terminal. So none of these are in the form. So what we do is, let's say in order to bring it into the form, I'll introduce a new non-terminal. So let's say B is a non-terminal that gives B. So now if I want to rewrite everything in terms of this terminal, in terms of this new variable b, how will we write that? So this becomes s gives a s b and s gives a b, and you have s gives b b. So now after this one step of modification, let's see whether the grammar is already in the GNF form. So here you have a terminal followed by product of non-terminal. So this is already in the GNF form. Then you have a terminal followed by non-terminal, that is also in the GNF form. And similarly the third one is also in the GNF form. So in this case we did very minimal modification. That is just by adding this one more production, we could manage to convert the grammar into GNF form. So this is the final grammar. If this is G prime, then G prime is equivalent to the original grammar G, but G prime is in GNF form. So the number of productions that we added is 1. So that's your answer. Okay. So yeah, I hope this is clear. Okay, so now yeah, so that covers all of the context free grammars that we wanted to talk about. Now we will talk about a model. So just like in case of regular grammars, regular languages, we had a corresponding model that captures the language. So if this is regular language, then you have a model which is DFA or NFA or 2DFA and so on. We saw lots of models that were equivalent. Similarly, you have, this is your regular languages, and we know that the string 0 to the n, 1 to the n, for example, is not regular. So it this language is not regular. So this lies outside this set somewhere here, but we already saw that there is a context free grammar for this, so it should lie in the context free languages. Okay, so this is the picture. Now yeah, now we define a model corresponding to it. So this is called push down automaton. Or a PDA. And what we will show later is that PDAs are capture the context free languages exactly, so they are equivalent in that sense. So yeah, so we'll look into it later, but let me define the model. So okay, so yeah, a push down automaton is basically uh, your DFA, but it has more power. So DFA does not have any memory, in that if you are at some state and if you read some letter, what you do is you just move to another state and you don't remember what you had seen in the past. So it does not have any memory in that sense. So push down automaton is a stronger version of DFA where you have some memory. So the memory that you have is in the form of a stack. So let's say you have a stack here, and suppose suppose z is the content that you have, and what you can do, the operations that you can do over the stack is you can push some content and you can pop some content, but you can do these modifications only at the top. So for example, if the content in your stack currently is 0 1 1 0 and you want to push something, let's say you want to push another 0, you can push it at the top. This is allowed, but you can't really push it somewhere here in the middle. So yeah, and similarly, if you want to pop out an element from the stack, you will have to pop it out from the front. So yeah, so those are the rules. So I hope stack I hope stack as a data structure, or as a model, is clear to you. So if that is clear, what we'll do is we'll now define what is a push down automaton. So so what a push down automaton does is you have a set of states similar to the regular languages. You have some symbol, input symbol. Okay, so I'll maybe write it here. So you have, sorry, yeah, so you have set of states, then you have sigma, which is input alphabet, then you have gamma, which is the stack alphabet, then you have a transition function delta, and we'll define what the delta is in a while. Then you have a start state as earlier, and you have yeah, you have a final state. That's how we will define the acceptance. So this is the, okay, so this is the model that you have. And for the only thing, okay, so this is the start state and this is the final state. So there could be multiple states, so technically maybe I could write it as f also. Okay, so this is possible. And only thing that I've not yet defined is what is the transition function, so delta. So let me define that. So delta is defined as a function from q cross sigma cross yeah, cross the gamma to q cross gamma star. So yeah, so basically what this means is, if you are in a particular state, this is what is the first this is what the first element in the tuple tells you. And if you read a particular symbol, let's say 0, then hi, um, yeah, so so just to connect you, we are talking about a model called push down automaton. So yeah, so I'm just defining it. So you have, this is given by a 6 tuple, and here q is the set of states. This is similar to the regular languages where you have DFAs with q as set of states. Sigma is your input alphabet, this is your start state q0, and this is your final state. Additionally, you have this one more element, which is gamma. So what is gamma? Gamma is basically all the elements that you can write on the stack. So in case of DFA, you do not have any stack, you don't have any additional memory, but this is an additional memory that a push down automaton gives you. What you can do here is, throughout the computation, you can push several values in there and you can pop out several values out of there. So this is same as the data structure stack that you might have seen, where you can push an element at the top, and you can pop out an element from the top, but all the operations that are there can only be done on the top. So now if all of the other things are clear, so this is the set of states, then you have alphabet, and you have start state and final state. Then how do we define the transition? So if you are at a queue and you see some alphabet here, then you say that, okay, look at the content on the stack. So if the content, let's say, is 1, then you should tell me where to go. So in this case I'm just telling you stay at q, because this arrow is clearly at q, and gamma star tells you what to write on it. So let's say if I see a 1, then I just want to write push 1 on top of it. So if initially there was some content and 1 was the top, the top letter element, what this tells you is that you pop this one out, then your content looks like whatever was here, say w, and now you're going to push 2 ones on top of it. So that's basically the transition. So it will become clear once we do some examples. So the only thing I want you to remember is that push down automatons are not very different from the DFAs or NFAs that you saw. Okay, so actually this should be a superset. Okay, so push down automata are not really different from the DFAs that you saw, because Yeah, I mean, as per the definition of the tuples, we have everything as the same, only that there are two changes. One is that you have a stack, and in order to differentiate the letters between the word and the stack, you have another alphabet, you have a different alphabet for the stack, and therefore we modify the transition function accordingly. It just tells you where to go, what to write on the stack, whether to write, whether to push, or whether to pop. That's the only thing it does. So yeah, so once that is clear, I just want to talk about acceptance condition. So when do we accept? Okay, so when do we accept? There are two yeah, there are two ways. One is that this is called accept by empty stack, and okay, and the other is acceptance by and the other is called acceptance by empty string. So what you do here in acceptance by empty stack is uh, throughout the computation you keep on pushing and popping several things here, and yeah, and you keep on popping, and at the end, if you if you have reached the end of, so let's say this is your input string, so you have x1, x2, and so on up to xn, and once you process the entire string, if at the end you have reached the bottom of the stack, so this is the this is the top of the stack and everything else is popped out, and you have finished reading the string, then you should accept. So that's what it says. And what is acceptance by empty string? It just says that if sorry, yeah, so yeah, it just says that if you have finished reading the string, then no matter what state you are in, you're going to accept. Okay, so we'll see, in fact it turns out that both of these notions are equivalent, and we'll try to see examples where uh, both of these are used. Okay, so okay, even if I mean, this was just a recap based on what was done in the lecture. So what we'll do is we'll look at some examples now. So okay, so here you are given a language which is of the form L is equal to 1 to the n, 0 to the n, 1 to the m. And m is greater than n plus 2. So for example, strings like 0, 1, 1, 1 would be in the language, but strings like 0, 0, 1, 1, 1 would not be in the language, because the number of ones here is not strictly more than the number of zeros by a factor of 2. So yeah, so this is not in the language. That's it. So the question is, you want to okay, so one thing to note here quickly is that you can always design a context free grammar for this. So for example, we have already seen plenty of examples like this. For example, for strings like this, we simply showed that s is s, um, yeah, s is 0, s1 followed by epsilon. So this would give you all the strings of the form 0 to the n, 1 to the n. Okay, so here the language that we're talking about is just this. but greater than equal to. So you can just simply modify the grammar slightly to say that S gives AB, where A is responsible for producing equal number of A is responsible for producing equal number of zeros and 1, and B is responsible for producing at least at least 3 more ones after this. So yeah, you can verify this later. So what we know for sure is that the given language is already a CFG. So this is a CFG corresponding to the given language. Now what we're going to do is uh, we will give a push down automaton for the same language. So I'll maybe wait for some time for you to think, and we will discuss in a minute. Okay, so let's look at the answer. So how the idea is, let's define the informal idea first. So what is the informal idea? Informal idea is that how are we going to use this tag? Hi. So how are we going to use this tag? Um, so that it accepts accepts the strings of this form 0 to the n, 1 to the m. So let's look at our stack. Initially it only has Z on the top, and everything here is empty. So what we will do is, because we want to make sure that the number of ones is at least 3 more than the number of zeros, what we will do is we will forcibly push 3 zeros at the top. Now the string that is given to you is some zeros followed by some number of ones. So let's say these are n, these are m. Now what we'll do is we will start reading the string. So if you see a 0, you push it at the top, then you move to the right. If you see another 0, push it at the top. So at the end we would have pushed n many zeros here, and we've already forcibly pushed 3 zeros here. Now our input, we have already read all the zeros. Now we come to 1. So what should we do? We want to somehow make sure that the number of ones should at least be this size. So there should be at least these many ones, n plus 3 many ones. So how do we do that? What we will do is we will start popping out. Okay, so if you see a 1 in x, you will pop this out. Then if you see another one, we will pop this out, and so on. So what will happen is, if the number of ones is more than n plus 3, then after n plus 3 steps we would already have reached the bottom of the stacks, because for every one that we saw, we popped out a 0. And if there were at least n plus 3 many ones, then we have popped all the n plus 3 many zeros from the stack. So now we are here, somewhere here. What we will do is, we will simply accept at this point, because we checked that number of ones is more than number of zeros plus 3. So if you reach bottom of the stack, which is Z, then accept. But the other case that can happen is, suppose the number of ones is lesser. So for example, let's look at the string 00111. So let's see how our example does it. Okay, one thing is this is not in the language, because number of ones is 3, number of zeros is 2 and 3 is not more than 2 plus 2. So this is not in the language, so our algorithm should not accept it. So let's see what happens. Suppose z is there at the top. Now we will read this 0. Okay, before that we are just forcibly putting 3 zeros on the top. Now we will read this 0, put it on the top. We will read this 0, put it on the top. Now we are encountering 1. So now that you see this one, we will pop this out. So now the top of the stack looks like this. Now you will see next one, and we will pop this, sorry, now we will pop this guy out. So the top of the stack looks like this. Now we will see this one, and we will pop this element out, and now the top of the stack looks like this. But we've not reached the end of the input. That is what happened. We've read all the zeros, we have read all the ones, we have reached the end of the input, but the top of the stack is 0, which is not set. So our algorithm will not accept, does not accept. Let's look at a positive example. So let's say 0 1 1 1. This is the string in the language because number of ones is 3, and okay, actually there should be one more. Okay, let's look at this. And number of zeros is 1, so number of ones is more than number of zeros plus 2. So this is in the language. So let's see what our automaton does. So this is the stack, then we are forcibly pushing 3 zeros. Now we will read this 0, we will push it at the top. The zeros are done. Now the next letter that we see is a 1. So what should we do on seeing a 1? We are just going to pop. So on seeing this 1, we will pop this out. So stack looks like this. Then you see this one, and again we do the same thing. We will pop whatever is there on the top. So this guy will be popped out. Then we look at the third one, and this guy will be popped out. And when we look at this one, this guy will be popped out. So now what happens is you have already finished reading the input, and we've already reached the bottom of the stack. So in this case we will accept. That is what the algorithm does. So basically you push 3 zeros at the top, then you all the zeros that are there in the input will be pushed. Once you start seeing ones, we will start popping, and if we reach the end of the stack in the process, then we accept, otherwise we reject. So is the algorithm clear? I will write this formally in the form of PDF, but is the informal idea clear? Okay, if there is something, if there is some doubt or there is some part that you want me to repeat, please let me know in the chat, or you can unmute and tell me. Okay, so let's see the algorithm that we described. We will just write a PDF for it. So let's see how to give push down automaton. Push down automaton for L. So what you do is, you are at this state Q0, and what we are going to do is, like we said, we are going to push 3 zeros on the top forcibly. So this is, if you read you read nothing, but the currently the stack is like this. You read nothing and you see a Z at the stack, then you are going to push a 0. So then you go to new state, and so now we have pushed 1 0. Now we should push 2 more zeros. So what you do is, if you see nothing in the string, and you see a 0 at the top, then you should push 1 more 0. So this is what it looks like. Then you go to state Q2, and you do this for the third time. If you see nothing but 0 is at the top, then you are going to push 1 more 0. So this part takes care of forcibly adding zeros. Now we will start reading the string. So let's say the input is x1 to xn. Now we will start reading the string. So what we do is, Yeah, now you are at Q3. If you see some number of zeros, then we are just going to push it on the top blindly. So that is what we will do. So you are at Q3, and if you see some zeros, then the top of the stack is 0, then we're just going to push the zeros. So this part is okay, add 3 zeros. This part is push all zeros. And now what we want to do is, once we are done reading all the zeros, now we will start seeing the ones. So let's say you are done seeing all the zeros here and the ones start here. So now what we want to do is, once we see a 1, we're going to pop out whatever is on the top, that element we will pop out. So let's see how to do that. So from here, if you see a 1 in the string and the top of the stack here is 0, so what we should do is, this epsilon tells you that you should pop out. So if you see something of this form, I'll just write it here. Note, if you see a 1 0 epsilon, then this just means that you are pop operation. That's it. So okay, so then what we do is, we have popped out, but that is not enough. Now we will read all the ones and we will start popping them. So if you see any number of ones, then we are simply going to pop it. Now what happens is, at the end of this, if we are done reading all the strings, and the last year, I mean, you can just imagine any string with lot of epsilons in between, so that is always the case. So if you're done reading this, you can just think of the last, I mean, empty strings following that. So if you read an epsilon and you've already popped out everything, that means your stack looks like this. Whatever was there, we popped out, so the top of the stack is Z. So if you see a Z, then let's see, we just write Z and we're going to accept it. So this is Q5. So yeah, I think I'll just write one more thing. So this is pop zeros. So yeah, so that is basically the automaton that you have. And in this case, what we are doing is, we are doing acceptance by empty stack, because what we did is, okay, so in that case, okay, maybe we'll write uh, pop the set. So in this case, what we did is that we yeah, this in this part, we just simulated the informal idea that we had. So we started at Q0, then this part pushed 1 0 on the top, this part pushed one more 0 on the top, this part pushed one more 0 on the top, and at Q3, when we reach Q3, we already have pushed 3 zeros. Now at this stage, what we do is, we are going to push all the zeros that you see. So in the given string, whatever zeros you see, you are going to push it. Now once you see ones, you start popping it. At Q4, we will pop all the ones, and at the end, if you are done reading the string and your stack is empty, then we are going to accept at Q5. So in this case, what we did is, we did acceptance by empty stack, but you can also use same idea to show acceptance by empty string. So I'll not get into it for now, maybe not for this example, but for some other example we may see. So that is the push down automaton for the given language. I hope this is clear. If there are any questions, please ask. If you want me to yeah, repeat any part, please do ask. Okay, so I think it is clear. So we will do one more example. So here you are given language which is 0 to the m, 1 to the n plus m, followed by 2 to the n. So the sigma is, so sigma here is 0 1 2, and the string accept, the language accepts strings of the form 0 to the m, 1 to the n plus m, 2 to the n, mn is greater than equal to 0. So just to see simple example, so for example 0 0 1 1 1 2, this is in the language, but string of the form 0 1 1 2 2, this is not in the language. So that's it. So basically the number of zeros plus number of twos should be equal to the number of ones, which is there in this case. So you have two zeros and 1 2, so totally we have 3 copies, so it matches, so that's the only thing. So I hope the language is clear now. I'll wait for a minute for you to try writing the PDA. If you have any answer, you can share it with me, otherwise we will anyway discuss. So I'll wait for a minute. Okay, so let's discuss the answer. Okay, so let's like earlier, what we will do is we will try to see an informal idea, and once the idea is clear, converting it into a PDA is not very hard. So we will see informal idea first. So what is the informal idea? You uh, yeah, let's say this is the stack. Let's say this is the stack that is given to us, and initially there is only z in the stack. What we do is we are given some string with m zeros, n plus m ones, and n many twos. What we do is, once you start reading the zeros, we're going to push all of them. So if you see 0, just keep on pushing. So at the end we will have m many zeros on the stack. Now what you do is, once you see ones, now all the zeros have been read and all the zeros have been pushed on the stack. Now you start seeing 1. If you see a 1, what you do is, we're going to pop a 0. You see a 1, we pop a 0. So I'll write this informally. So step 1 is push all the zeros on the top. Second is pop zeros on seeing, pop a 0 on seeing a 1. Okay, so yeah, so if there are n many zeros, m many zeros, and there are n plus m many ones, then on reading m copies of ones, the stack will become empty. So if there were 3 zeros, let's say, then on seeing 3 ones, this thing will go away. We will pop out all of them, and the stack is again empty. But there may still be some ones following that. So there may be n many ones after that, because total number of ones is n plus m, and we have only seen m many ones. So there are still n ones that are still there. So what you do now is, so all these are popped out. So this is what it looks like. Now what we do is, now we start pushing the ones. Okay, so how many ones will be there? There will be n many ones, because totally there are m plus n, and m of them went away because we popped the zeros because of it. So there are n copies of 1. So now you start push ones on the stack. And now what we do is, now we have read all the ones, we start seeing 2s. Once we start seeing 2, we are going to pop out 1s. So this is what we will do. So now pop 1 from the top of the stack on seeing a 2. So if this happens, then what will happen at the end of all, at the end when you read all the 2s, all of the 1s will be popped. So the stack will again become empty. So see if the stack is empty, then If the stack is empty, then accept, otherwise reject. So that is a simple intuitive algorithm. What you do is you first push all the zeros, keep popping ones. So that means equal number of zeros have been removed. Now you just want to see that there are equal number of ones and twos. So you do the same thing. Keep on high. So keep on pushing the ones and keep on popping the twos. So that is the informal idea, which is something you would have thought about. So what we will do is we will just convert this formally into a PDA. So the same idea, but I will write it in the form of a PDA. So yeah, so maybe I'll take a new page. Okay, so the given languages: 0 to the m, 1 to the n plus m, 2 to the n, where n comma m is greater than equal to 0. So what we will do is, we are at the start state. Okay, so I'll just write the notation here so that it's clear to you. When we say 1 0 does something, this is the input we are reading, this is the top of the stack, and this is what we are pushing. Okay, so this is just for reference so that these letters don't confuse. So initially the stack is empty, so there is only z at the top. So what you do is, if you read a 0 from the string and the top of the stack is z, what we want to do is we want to push the 0. So you write push the 0 and leave the z as it is. Okay, then what you do is, if you see more zeros, now let's say you saw a 0, you pushed it at the top. So now if you see another 0, the top of the stack is 0 here. So if the top of the stack is 0, you are still going to push. So at Q0 we would have pushed all the zeros. Now you start encountering, so all the zeros have been processed. Now you start reading the ones. So what we want to do is, we want to see that equal number of ones are there are equal number of ones and zeros, and we will balance them out. So now we want to start popping out once we see a copy of 1. So if you see a 1 and the top of the stack is 0, then you pop it out. So epsilon just tells you that you pop out. So this is Q1, and from here if you see more ones, then we are just simply going to pop out. So at Q1 what has happened is, we have exhausted all the zeros and we've removed all of them, so that the top of the stack at this point is again empty. Now there may be more ones that come up. So let's say there are more ones that come, and the top of the stack is empty, then you're just going to push it. Now the top of the stack is a 1, there may be more ones that are coming. So yeah, so here you are just pushing all the ones, and then you may start to encounter, once you have pushed all the ones, now you start seeing the 2s. So if you see a 2 and the top of the stack is 1, then we are going to start to pop out. So this is what we will do. You go to Q3, and if you see more 2s, we are simply going to pop out the ones. Now let's say in this process we have reached the end of the string. So if you see epsilon and the top of the stack is empty, then we will accept. So this is again acceptance by empty stack. So let me just recall what we did. We started with the state Q0. We started pushing the ones here. Whether the stack was empty or whether there are elements on the top, as long as you see a 0, we're just going to push all the zeros. Then once you start seeing ones, we're going to pop the zeros so that the number of zeros and ones are balanced out. So this part we just popped out all the zeros. Now again the top of the stack is empty, but there may be ones here because this is where we are. So there may be still some more ones that are to be read. So this is just that we are pushing all the ones. So in this part we are just pushing all the ones, and in the last part we just want to see that the number of ones on the top of the stack and the number of 2s remaining in the string, are they equal. So in this part in this part we start popping out the 2's, and at the end if we have finished reading the string and and the top of the stack is empty, then you're just going to accept. So this is acceptance due to the empty stack. So I think I'll let you stare at the PDA for a minute. If you have any questions or if you want me to repeat any of the part, please do let me know. Okay, so if there are no questions, I think I'll move on to the next question. So this is a slightly more interesting question. It's of the similar kind, but here you need to do something more to make it work out. So yeah, so the language that is given is a to the 2n, b to the 3n, where n is greater than equal to 0, and what that means is the number of a's should be a multiple of 2. So you can have 4 ones, 4 a's, you can have 6 a's, and so on. But yeah, okay, and let's say n is 2 for us because 4 is equal to 2n. Okay, then how many copies of b should be there? You should have 3n copies of b, which is 3 times 2, which is 6. So this is, yeah, so this is in the language. But let's say for example a b b b, this is not in the language because the number of a's is 2n, then n is 1. So how many b should be there? Okay, sorry, I think I took a wrong example. Let's say there are 4 copies of b. So how many b's should be there? There should be 3n number of b's, which is 3. But in this case we have 4 b's, which is not equal to 3n, so this would not be in the language. So that's it. So you should have that twice the number of a's is equal to the should be equal to thrice the number of b's. So yeah, so that is the question. So I'll let you think about it for some time, then we will discuss this. Okay, so okay, let's discuss the solution. So I'll again do the same thing. We will start with informal idea. Okay, so what is the informal idea? Okay, what we will do is you have an empty stack. What we will do is for every a that you see, we're going to push three copies of a into it. So for example, if your string is a b b b, what we will do is for the first a that you read, we will push 3 copies of a. For the second a that you see, we will push 3 more copies of a. For the now you are done reading the a's. Now if you see a b, what we will do is we will, for every b that you see, we will pop 2 a's. So if you see 1 copy of b, we're going to pop this, we're going to pop this. For the second copy of b, we're going to pop this and pop this. For the third copy of b, we're going to pop both of them. So at the end, when you have read the entire string, you would have reached the empty stack. Your stack would be empty. So that's the whole idea. For every, so let me write it. For every a, push 3 a in input. push 3 A's on the top of the stack, and for every B in the input, push 2 copies of B on the stack. So why does this work? So if the number of A's is 2n, how many A's would be there on the stack? There would be 3 times 2n many A's on the stack, which is nothing but 6n. Now suppose the number of B's is a multiple of 3, which is 3n, and then we're popping 2 symbols out of it. So this would also be 6n. So for 6n letters that were pushed on the input, we are popping out 6n many A's. So hence at the end you would reach the empty stack. So that's basically the idea. It's just that you here, instead of pushing one letter on the top of the stack, we are pushing a string. That's the only difference. So I'll if the informal idea is clear, I'll write this PDF formally. So if there are any questions about the informal idea, please let me know. So let's say you are at Q0 and yeah, so let's say you are at Q0 and you see 0. What you do is, so you see an A, what you do is, if you see an A and the top of the stack is set, then what you do is you push 3 A's on the stack. Okay, similarly if you see an A in the input and the top of the stack is A, again we're going to push 3 A's on the top. So this is what it looks like. Now yeah, now let's say you are done reading all the A's and you start to see a B. What we do is, if you see a B, yeah, if you see a B, you're going to pop two A's. So you go here, then let's say this is Q1, and here also you will be sorry, we don't read anything. Yeah, you don't read anything, but you are going to pop. Okay, maybe I'll do it this way. So you don't okay. Sorry. Yeah, and now again you don't read anything, but if you see any, then we're just going to pop it. Now let's say we are at Q2. Now if you see another B, we want to do same as what we did earlier. So if you see a B, we just want to, and the top of the stack is A, then we're just going to pop it. And yeah, and we're going to come back here. So and we're going to come back here. So if you don't see anything, but the top of the stack is A, then we are going to pop out. So this loop basically takes care of the fact that for every B that you read, 2 A's are going to be popped out. So we only read one B, we popped out one A, then we only read we didn't read anything, but we just popped out an A. So this loop takes care of the fact that if you see a B, two B's are going to be popped out. And after doing this, if at the end we have finished reading the string and the top of the stack is empty, then we're just going to accept. So this is a final, so this is Q4. So this is the final automaton that we have. So you started here, and for every A that we see, we started pushing 3 A's. Then we made a transition. If you see a B, we popped out an A. And this is for making sure that one more A is popped out, because for every B we see, we're going to pop out 2 A's. And this loop is going to do the same thing again and again until we've exhausted reading the string and in that case, if the top of the stack is empty, then we're just going to accept. So that's the yeah, so that is the basic algorithm, and it's same as what we wrote in the informal side, but here we have it in the terms of the states and all. So I'll wait for a minute. If if there are any questions regarding the PDAs or the context-free grammars or the examples that we discussed, please let me know. Yeah, and yeah, we can discuss if there are any questions. Okay. So if there are no questions, okay. Is there a question?
Can you explain with an example?
Okay, yeah, sure, sure. Okay, so let's keep the automaton here, and we will. Do you have any example in mind? Any input string?
Uh, Suppose if you take n value as 2,
Okay, n is 2, then you have. So this is a to the 2n.
4 A's.
Yeah, you
4,
have 4 a's, and you have 6 b's.
yeah.
Okay, so at the beginning, the top of the stack is I mean there's nothing on the stack, it's empty. So what does q0 tell us? Q0 says that if you read an a in the input, so which is this a, and the top of the stack is z, then we are just going to push 3 a's. So this is what we will do. This a is read, then you see the second a, and we are in this case. So if you see an A and the top of the stack is A, which is what we have here, we're going to push 3 A's. So you have 3 more A's. For the third A that you read, this will happen again. You will have 3 more A's. Okay, I'll get this below. 1 second. Okay. So for the fourth A, we will again push 3 more A's on the top. So this is what we have. So there should be 3 into 4, which is 12 A's. 1, 2, 3. Okay, so now so now we are here, and we are done reading all this. Now the next input that we see is a b. So if we see a b in the input and the top of the stack is a, which is what we have here, we're going to pop it. So we will simply pop out this one.
Okay,
Then
understood. Understood, madam.
okay, sure.
Thank you.
Sure, thank you. Okay, so yeah, um, okay, I'll take this example. So here yeah, we know that context free we saw the context free languages. This is what the CFG recognizes or what a PDA recognizes. So the question is, under which of the following operations is are context free languages closed? So any any ideas?
It's closed under union, concatenation,
Right,
clean star,
sure, yeah. uh,
mm, union, concatenation, clean star, and mm, I know about only these three: clean star and clean closure, union, and concatenation.
Okay, sure. That is right. In fact, it turns out that it is only closed under clean star, union, and concatenation from the given examples. It is not closed under intersection and complementation. So, how do we show, for example, if it is closed under clean star? How do we prove this? The closure.
Uh, by including an epsilon.
Mm, okay, in terms of PD, we can do that. If you want to do in terms of grammar, okay, maybe like if we just want to do union using grammar, we want to show that it is closed under union. So,
Yeah. S
uh,
is equal to S1 or S2.
yeah, exactly. That is correct. This is a simple thing that we will do. If it is
Yeah.
concatenation, we will do S gives S1 S2.
S1, S2.
And yeah, and if we want to do
Mm.
clean star, what we will do is S gives
Uh,
um, S1S or
S1,
S1.
S. Yeah.
Yeah, so you can do the same thing using PDAs also, like you said, by adding appropriate transitions, but it is very clean to see in terms of CFGs. And for intersection, um, okay, so this thing, I think pumping lemma is not done yet, so later on we will see that uh, 1 to the n, okay, let's say 0 to the n, 1 to the n, 2 to the n. this is uh, this is a language which cannot be um, I mean, this is not in the this is not a CFG. Okay, and you can write this in terms of, you can write this as an intersection of two languages. So we can write this is 0 to the n, 1 to the n, uh, 2 to the m, where, okay, maybe I'll write lmn, sorry, lmn, where n is equal to m. So this is the first language, and the second language is 0 to the l, 1 to the n, 2 to the m, where l is equal to m. So observe that L1 intersection L2 is nothing but this L, because L1 takes care of the fact that number of ones is same as number of twos, and L2 takes care of the fact that number of zeros is equal to number of twos. So if we take intersection, all of them will have to be equal, right? um,
Mm-hmm.
so but for L1 and L2, we know how to get context free grammars. For
Yeah,
example,
yeah.
yeah, so these two are context free, but if you take intersection, it turns out that this is not context free, so these languages are not closed under intersection. And if it is not closed under intersection, what can we say about complementation?
I think it is not closed under complementation, I think.
Yeah, that is right. Because we know that by De Morgan's law, we know that L1 union L2 is nothing but L1 intersection L2 complement. Now, if L1 and L2 are context free, then this is also context free.
Mm.
And this is not context free. Okay, basically, this is same as
Mhm.
complement
Okay.
of this is this. So, this is not CFG. And if it were closed under complement, then we would get a contradiction that this is context free, but the right hand side, which is equality, is not context free. So it can't be that it is closed under complement. Is this okay?
Yeah, yeah.
Okay. um yeah, so I'll take this question. So this is again a closure type question, but under an operation called reversals. So um, yeah, basically if the string is 0 0 1 1 1 0, then the reverse of it is 0 1 1 0 0. Just
0,
so this is just that you look at all the strings in the language and reverse them. So the question is the context free language, the class of context free language is closed under reversals?
Mm. Don't know.
Okay, sure. So we can think about it in terms of PDA also, but again, in this case, it so happens that thinking in terms of
Yeah, it
context,
is. Yeah, it is closed. I think it is
yeah,
closed under reversal.
yeah, that is right. What are your idea? What is your idea?
Uh, in PDA, it can accept W and W to the power of R.
Hmm, hmm.
Uh, it is possible to be considered the PDA for W followed by W to the power of R.
Okay.
In that case, I'm going to be say that it is also closed under CFL. If suppose I'm going to be construct
Mm-hmm.
S tends to that is an if I'm going to be take the string
Mm-hmm.
AABB.
Okay.
W is AABB. W to the power of R is BBAA.
Yeah.
Yeah, if it is possible to be construct CFL for AABB, and also it is possible to be construct the CFL for W to the power of R also.
Yeah, that is right. But sometimes the language may be little bit more complex, so there could be like different kinds
Mm.
of strings in the language. So
Yeah.
yeah, I mean the idea is correct, but it's
Mm.
just that it is not complete. So
Okay.
um, we can talk about it in terms of PDAs also, but since it's easy, it's more natural to think in terms of CFG. First, I'll do it in terms of CFG. So
Mm.
let's say this is the grammar that we have.
Yeah.
So this is
Yeah.
yeah. So this is nothing but 0
Mhm.
to the n, 1 to the n greater than equal to 0. Now if I just
Mm.
reverse all the production, so what I mean by that is you look at this, write the string in the reverse order. So this is 1 as 0 and this is just epsilon. So s
Mm.
prime is 1 as 0 or epsilon,
Or epsilon. Mm.
then this is 1 to the n, 0 to the n. And it's
Mm.
not just for this, it happens if even
Mm.
if you have very complex grammar, if you just reverse the order, what happens is, let's say you had s gives a b, then you had a gives b b, let's say, and this is c, this is some c. Let's say this is the grammar we had. What we are doing here in terms of parse tree is that we are just looking at this and reversing it. So in this case, s will give b a, then
Mm.
this b is just giving c. For this a, it is bb. So if we reverse it, it becomes small b followed by capital B, and b just gives c. So if this string was a b c c, then this string, okay, is there something wrong? Uh, Oh, I did not reverse. Sorry, sorry. This is small b, capital B, then the reverse would be capital B, small b.
Yeah.
Yeah, so capital B gives small c, so the string that you get is CCBA. So basically, what we're doing is for every production, we are just writing a reverse of that. So the order in the past tree gets flipped. That's why if you have a grammar for yeah, if you have a grammar for a language, you also have a grammar for the reversal. Okay, so maybe I'll just write what we did is, if you have a production of the form a gives abc or something, we're just making it cba whatever. This is for all the production, so the resultant grammar would be a grammar for reversal. uh,
Mm.
this Okay, so the thing that you were saying about PDA, that is also, the intuition is correct, but it will take a little more work. So like in case of NFS, we showed that it is closed under reversal. What we did is, if if there is some NFA that goes like this, and let's say this is the final state, what we did is we flipped the transition. So if you have transition from A to Q1 to Q2, we flipped the transition in the reverse direction. This we did for all of them. And uh, ultimately if you can reach this state, then basically we are accepting the string. So this was our final state. Whatever is the start state, in the reversal we make it a final state and collect all the accept states and make this your start state. So for example, if this was NFA that um, um, let's say this was the NFA, then what we are saying is uh, make Q1 your final state, reverse the order of transitions, and make this your new start state. If there are more
Yeah.
final states, then yeah. So it's the same idea, but just that we have to take care of the stack, the values on the stack, so that will just take little more work, but the
Then
idea.
here we are going to be making final state as the start state.
Exactly, yeah.
If more than one final states are there, what we should have to do?
Yeah, here if there are more final states, like in this case, in this case we will
Mm.
add one more state, make it a start state and make an
Okay,
epsilon
epsilon
one.
transitions. Okay. Mm.
Okay, so the same
Mm.
idea will work for PDS also. um, okay, so yeah, I'll take one more example. So this is a variant of the PDA. So in case of push down automaton, we had uh, a stack like this where we can push and pop at the top. Now what we are saying is, consider a different model where instead of a stack you are given a queue. So let's say this is a queue, and what are the operations that you are allowed? You can push it from the front, you can keep on pushing in the front, and you can pop out elements from the back. So like in case of stack, you just push and pop from the front. Here you push from the front and pop from the stack. So let's call this model PTA. Now the question um, is we want to show that if okay I mean basically um, this is nothing but W followed by W for W in 0 1 star. Okay, so this is the language that we have, and we want to show that there is a PTA with a there is a queue and a uh, corresponding transition diagram which will accept this language. So how do we show that? Is the model clear?
Hello.
Hello. Yeah, sorry, if you were speaking I couldn't hear.
Okay. What you are asking?
Yeah, so the push down automaton as a model, it has a
Yeah,
stack,
yeah, yeah,
and
yeah. I know that.
oh,
That
okay,
is
sure.
nothing. But we are, instead of using stack, we
We
are
are
going to be
using
using the
a queue.
queue.
Yeah.
Okay.
So the question is, for
Mm.
this language, can we
Mm.
give a push through automaton which uses a queue instead of the stack?
Mm-hmm.
I mean, just
Okay.
informal idea would be okay.
Okay. You only explain it.
Yeah, sure, sure. Okay, I'll do the B part first, that is the harder one. And once that is okay, so a to the 2n is basically I mean number of a's with which are power of 2. So for example, a, which is a to the 2 to the 0, then a to the 2 to the 1 is basically just 2 a's, and 4 a's, and so on. So if we want to we want to accept only if the number of a's is a power of 2. So what we will do is, um, this is the stack that you have, and what we do is, initially we are just going to push all the a's inside. So let's say these many a's were there in the given input, and we will just push all of them. Now we want to check whether it is a power of 2. So yeah, so what we will do is, for okay, just give me a minute. Okay, okay, yeah, okay, so what we will do is, we know the property of powers of 2. If a number is a power of 2, then if you divide it by 2, it is still a power of 2. So again, if you divide it by 2, it will still be a power of 2, and eventually you will get to 1. Okay, that is the whole idea. So what we're going to do is, given um, k many ones, k many a's, we want to make some modifications so that in the resultant stack there are only k by 2 many a's, like this. Okay, in the next step we will make them k by 4, and at the end, if we can get to 1, then that means the number is a power of 2. Otherwise, if a number is not a power of 2, if you keep on dividing by half, you will never get to 1. So that's the idea. So how do we do that? So let's say this is the queue, and we have pushed all the a's. Sorry, we have pushed all the a's. Yeah, so now what we will do is, you pop one element from the back, and put a b here. Okay, and pop one more element from the back. Okay, basically you pop two elements and put a b, then you pop two more a's from the back and put a b. So basically, for every two elements that I'm popping, push one b. So what will happen is, if you pop k many a's, then how many b's will be there in the front?
K by 2.
K by 2. That's right. So what will happen is, after this step you will have k by 2 many b's. Now we again want to do the same thing. Now we will pop 2 b's and push 1 a. Okay, so at the end of this process we will have k by 4 many a's, and we keep on repeating this. So at the end, until you see one element. So at the end, if you see a 1, yeah, I mean, you will conclude that it is a it is a power of 2, otherwise it is not a power of 2. So yeah, that's the only idea. And yeah, I think, yeah, that is all I had for, that is all the questions I had for today. The other one that I wanted to discuss is about right linear grammar. So I think I'll take it up in the next tutorial. Okay, so
Yeah, let me know how to construct that PDF for this.
like the diagram.
Yeah, yeah.
Okay, I haven't thought about it, but okay, maybe I'll think about it right now. Um,
Okay.
okay, basically, we want to have some notation for uh, pushing and popping. That's it. Okay, so let's say you start at Q0, and we just want to push all the A's. So if you see, Okay, maybe let's say that um, there is some star element that I mean, which just tells you that there is nothing in the beginning. So if you see a star, then we are going to push. Yeah, we're just going to push it. And if you actually, we don't even need this because it is not a stack. Okay, sorry.
There may be blank spaces, maybe.
If you're thinking of it
In
as a tape, yeah. If you're thinking as a
paper.
tape, yeah. Yeah, actually, it turns out that this is as powerful as Turing machines. So,
Mm.
yeah, it's basically the tape thought of it with the restriction. So, okay, maybe let's go with that. So, if you see a blank symbol, just write an A, and if you see A's, we just write an A. So, by this, we have just written the A on the stack. That's it. Now, what we do is we okay. I think if this is what I'm just using this notation to say that we are popping an A and um, pop one more A
Mhm.
and then we push a um, okay, actually we don't even need to read this, right?
Mm.
You're just pushing it
It is
anyway.
not
Yeah, so you
just push and pop up.
so just push and pop. So you're just going to push an A. Okay, I really don't have a good notation right now, but okay, then what sorry, we should push a B, and there will be a loop like this. So pop A, pop A, and okay, this is enough, right? If we do this,
Mm.
we are popping two A's and pushing one B, and yeah, and now we want to repeat this for B's as well. So at this point, um, okay, I think I don't have any good okay, I need to think about it.
Okay.
Okay, thank you for the question.
Okay.
um,
Thank you.
okay, so I think I'll stop the recording.
Okay.
Okay, thank you.